This video is for Chemistry in the Earth System, Unit 5.1, the composition and behavior of the atmosphere. Today's essential question is, what effect does the sun have on Earth's atmosphere? Let's begin with one of the most important facts in Earth science. The sun is the ultimate source of energy for our planet. Without the sun, Earth would be a cold, frozen rock drifting through space. Life as we know it could not survive. Plants wouldn't photosynthesize, animals wouldn't eat or move, and there would be no weather or wind. The sun's energy drives atmospheric circulation, which is the movement of air around our planet, as well as the temperature patterns and weather systems that we experience. This energy keeps our oceans and atmosphere warm enough to support life. As we explore the sun's influence, we'll understand how it heats Earth's surface, moves air, and creates the patterns we observe in daily and seasonal weather. The sun provides nearly 100% of Earth's energy. This energy reaches us in the form of solar radiation, or electromagnetic waves. During the daytime, solar energy heats Earth's surface. At night, when this energy source is absent, temperatures fall, and sometimes dramatically. But not all of the sun's energy makes it to the ground. Earth's atmosphere acts like a filter, absorbing some radiation, reflecting some back into space, and letting only a portion through to the surface. This filtering helps protect life by limiting the amount of harmful ultraviolet radiation and helps maintain a stable climate. We see evidence of this heating effect every day in the day-night temperature cycle. For example, deserts, which lack clouds and vegetation, often experience extremely hot days, followed by chilly nights, showing how quickly energy can be lost or gained. Now, let's talk about how energy moves through the atmosphere. There are three main methods of energy transfer: radiation, conduction, and convection. Radiation is how energy travels from the sun to Earth. It doesn't require particles or a medium. It moves through space via electromagnetic waves. Think of sunlight warming your skin. Conduction occurs through direct contact between particles. For example, when you walk barefoot on hot sand, the sand particles transfer heat to your skin. This only happens when substances are physically touching. Convection happens in fluids, like air or water. It's the movement of heat by flowing materials. Warm fluid rises and cooler fluid sinks, creating a cycle. This movement is especially important in Earth's atmosphere. It helps distribute thermal energy from the surface upward. Together, these three processes regulate temperature and help drive weather. Now let's take a deeper look at convection, because it's one of the key processes that powers the weather. When the sun heats the ground, the air above it also warms. As the air warms up, it becomes less dense and expands. Because it's now lighter than the air around it, it begins to rise. As it rises higher into the atmosphere, it encounters cooler temperatures. That causes it to cool down and become denser, and then sink back toward the surface. This cycle, rising warm air and sinking cool air, is called a convection current. It's the same basic idea behind boiling water. Hot water rises from the bottom of a pot, cools at the top, and sinks again. In Earth's atmosphere, this creates weather patterns like wind, clouds, and storms. Understanding how fluids, like air, behave helps us explain atmospheric movement. When a fluid, like air or water, is heated, its particles move faster and spread out. This causes the fluid to expand, and its density decreases. Think about a hot air balloon. The air inside the balloon is heated, becomes less dense than the surrounding cooler air, and the balloon rises. But what causes the air to move? Gravity plays a big role here. Denser air has less mass. Denser air has more mass, so gravity pulls on it more strongly. As a result, cool, dense air sinks towards the surface and pushes warm, less dense air upward. This movement leads to differences in air pressure, which helps generate wind and large-scale atmospheric circulation. Not all parts of Earth receive the same amount of sunlight, however. This uneven heating happens for several reasons. Earth's curvature means that sunlight hits the equator directly but strikes the poles at an angle. At the equator, the same amount of sunlight is concentrated in a smaller area, making it much warmer than the poles. Land and water also absorb heat differently. Land heats and cools quickly, while water changes temperature more slowly. This difference creates temperature contrast between continents and oceans. Ground cover also varies. Forests, deserts, ice, and urban areas all absorb and reflect sunlight differently. And atmospheric transparency matters too. Clouds, dust, or pollutions can reflect sunlight, reducing how much energy reaches the ground. This uneven heating is the foundation of global wind patterns, weather systems, and even climate zones. One way to measure how much energy Earth's surface reflects is called albedo. A high albedo means most sunlight is reflected. Surfaces like snow and ice have albedos of 80 to 90%. A low albedo means most sunlight is absorbed. Forests and oceans typically have albedos around 5 to 20%. Albedos explain why ice-covered regions stay cold. They reflect most sunlight away. In contrast, dark forests absorb more heat, warming the surrounding air. Water's albedo depends on the angle of the sunlight, which is why oceans can be cooler at sunrise or sunset, but absorb heat more strongly during midday. When the sun heats Earth unevenly, it creates differences in air temperature. Remember, warm air is less dense and creates a low pressure zone. Cool air is denser and forms a high pressure zone. Air naturally moves from high to low pressure to try to balance things out. This movement is what we experience as wind. As warm air rises, cooler air rushes in to replace it. This movement sets up convection cells and global circulation patterns. These pressure gradients and movements form the basis of everything from light breezes to powerful storms. Have you ever tried throwing a ball while on a spinning playground merry-go-round? The ball seems to curve away from where you aimed. This is a demonstration of the Coriolis effect, the apparent deflection of moving objects due to Earth's rotation. On Earth, this means in the northern hemisphere, moving air turns to the right. In the southern hemisphere, it turns to the left. This effect doesn't cause wind, but it changes its direction, especially over long distances. This is why hurricanes spin counterclockwise in the north and clockwise in the south. The Coriolis effect helps organize our planet's global wind belts and storm systems. Our planet has a system of major wind belts created by the combination of the aforementioned uneven heating and the Coriolis effect. The trade winds blow from about 30 degrees latitude toward the equator. They are consistent and reliable, historically used by sailors. The westerlies blow from 30 degrees to about 60 degrees latitude. These are winds that bring much of North America's weather. The polar easterlies blow from the poles toward about 60 degrees. They're cold and less consistent. At high altitudes, we find jet streams, fast-moving rivers of air that circle the globe and help guide weather systems. Pilots and meteorologists track these winds closely because of their impact on storms and aviation. Besides global winds, local winds form in areas like coasts and mountains due to daily temperature changes. During the day, land heats faster than water. Warm air over land rises and cooler air over the ocean moves in to replace it. This is called a sea breeze. At night, the opposite happens. The land cools faster than the water, and now the air flows from the land to the sea. This is called a land breeze. Similar processes occur in valleys and mountains. These breezes impact local weather and are especially important in coastal and mountainous communities. Some winds are even more specialized and extreme. These are called katabatic winds, and they occur only in when cold, dense air rushes downhill due to gravity. So, the Santa Ana winds in Southern California are warm, dry katabatic winds and pass through mountain canyons. They increase wildfire risks by drying out vegetation. In Antarctica, katabatic winds are extremely cold and fast, moving from high, icy interiors toward the coasts. The Chinook winds on the east side of the Rockies are warm winds that can melt snow and raise temperatures rapidly. These winds are driven by temperature, elevation, and pressure differences and have a major impact on regional weather and safety. At this point, you should be able to generate a full and appropriate response to today's essential question. What effect does the sun have on Earth's atmosphere?